Today we're going to talk about what makes a single replacement reaction likely to occur using our New York State Reference Table, specifically Table J. Learning goals for this video include identify more and less active metals using Table J of the New York State Reference Table, explain why more reactive metals will displace less reactive metals in solution during single replacement reactions, and predict whether or not single replacement reactions will occur based on the reactivity of the metals in the reaction. As an added bonus, I will also give you an opportunity to write ionic formulas and to balance chemical equations. You're welcome. You probably recognize Table J of your reference table, the activity series. Table J tells us which metals are more active or reactive than other metals. Table J also describes nonmetals and their reactivity, but we're going to be focusing primarily on the left-hand side that's dealing with metals and hydrogen today. So what does it mean for a metal to be more active? When we say that a metal is more active or reactive, what we're really saying is that the metal is more likely to lose electrons and form a positive cation when it is placed in water. Basically, we're saying how likely is this metal to lose electrons and become an ion if we drop it into a solution. A more active or a more reactive metal is higher on Table J than a less reactive metal. The more active metal is more likely to lose electrons, especially when placed in water, than the less reactive metal. So, for example, we can say that lithium is the most active metal on the entire activity series because it is all the way at the top. Silver and gold are the least active metals on the activity series because they are all the way at the bottom. Where an element falls vertically on the table tells us how active it is. So the next question you may have is, why do we care if a metal is more reactive or more active than another metal? What's the big deal? So it turns out that lots of metals can form ionic bonds with nonmetals or with negative polyatomic ions and form ionic compounds. Some of these ionic compounds are soluble or dissolve in water. Turns out when a more reactive metal is placed into a solution of a dissolved ionic compound that contains a less reactive metal, the more reactive metal will actually replace the less reactive metal in solution. It ends up being pretty cool looking. We'll watch an example now. Let's look at copper chloride, which is a blue salt dissolved in water to form copper chloride solution. And we see we've got a clear blue liquid there. And let's add some aluminum foil to it, some solid aluminum foil. Now, as we speed up the reaction, so time is going to be sped up to 10 times as fast as it normally would be, we are going to notice a new product forming. So you may be noticing right now that there's this brown, dark brown, black looking solid that's forming and floating to the bottom. As a little bit more time passes, and again, this is sped up, you notice that the amount of aluminum foil seems to be decreasing. It's subtle, but if you really stare at the aluminum foil there, you can see that the amount of aluminum foil seems to be decreasing, especially if you look around the edges. And the amount of this solid seems to be increasing, this dark brown solid. It's particularly dramatic when I stir with a stir rod. So aluminum essentially didn't really disappear, right? Mass cannot be created or destroyed, but instead the aluminum actually dissolved. That solid aluminum foil became ions in a solution, dissolved into what used to be the copper chloride solution, is now becoming aluminum chloride. And we saw copper in the form of those little dark brown specks come out of the solution, precipitate as a solid. If we look at our activity series, notice aluminum is higher than copper on the activity series. aluminum is more likely to become an ion in solution than copper is. So when aluminum was added, it was more likely to become an ion and take copper's place. That's how the activity series connects to predicting whether or not a single replacement reaction will occur. So in that reaction, we saw solid aluminum reacting in copper chloride solution to form aqueous aluminum chloride and solid copper. Remember the word aqueous, that's the abbreviation AQ, tells me that the substance is dissolved. So that instead of being solid aluminum chloride, a solid salt, I have aluminum ions and chloride ions that are floating around in the water in solution. And copper is becoming the solid substance at the end. The unbalanced chemical reaction would be aluminum in solid form, so ALS plus CuCl2, copper chloride. CuCl2 is the correct way to write the formula for copper 2 chloride, reacts to form, that's the arrow, solid copper plus aluminum chloride. And because an aluminum ion has a charge of +3, right, reminding ourselves of our ion charges, I would write the formula for aluminum chloride as AlCl3. Now, quick review for you. I invite you to practice balancing this equation, and I'll put up the balanced version in just one moment. So the balanced chemical reaction would be 2Al plus 3CuCl2 reacts to form 3Cu plus 2AlCl3. Just a little bit of integrated practice here. This is a single replacement reaction because notice aluminum starts off on its own, single. Copper starts off in a compound with chloride. After the reaction happens, aluminum and copper have switched places. Copper is now on its own. Aluminum is now in a compound with chloride in our reaction formula. You are going to do some practice now. You are going to, first and foremost, decide whether or not a reaction will actually occur in each of these scenarios. Remember, to do that, you are going to look at the activity series and see whether or not the solid single element that is being added to the solution is more or less reactive than the metal that is already aqueous in the solution, that is already dissolved. So you're testing with table J to see which metal is more active. If the metal that's being added as a solid is more active, the single replacement reaction will occur. If the metal that's being added is less active than the metal that's already there, no reaction will occur. I invite you, if you want to be extra, if the reaction does occur, determine what the products of the reaction would be and balance the final equation just for an extra challenge for yourself. So pause the video, take a few moments to try these 6 practice problems using table J. Make sure you're giving yourself a chance to practice. I'm going to go over the answers now. I'm going to do this fairly quickly, focusing more on how I decided whether or not a reaction would occur. If you're confused about how I wrote the products, how I knew what those chemical formulas would be, or about how I balanced the chemical equations, look back at some prior videos when we talked about writing ionic formulas and balancing chemical equations, because that's just not the focus of our learning goals today. It's just some extra practice that we're getting. Question number 1 asked about solid iron being added to a zinc nitrate solution. So this is saying that solid iron has neutral atoms of iron being placed into already dissolved solution of zinc ions and nitrate ions. Remember, the more reactive metal is the one that will end up dissolved as an ion. Zinc was already an ion because it has AQ next to the compound that it is a part of. Zinc is more reactive than iron on the activity series. It's higher on the activity series. So zinc is already where it needs to be. It's the more reactive metal. It is already dissolved in solution, so no reaction is going to happen here. If this were the other way around, if zinc was coming in by itself and iron was with nitrate, then there would be a reaction. But because iron is coming in by itself and it is less reactive than zinc, it will not replace zinc in solution. Let's take a look at number 2, when solid sodium is added to zinc nitrate. So again, we're looking at zinc nitrate. Let's find sodium on the activity series and zinc. So in this example, sodium is higher than zinc. Notice how this is different than the last example. Iron was lower than zinc on the activity series. In this example, sodium is higher than zinc. So as the more reactive metal, it will end up dissolved as an ion. So it will undergo a single replacement reaction. So this is the formula that I end up with: zinc by itself plus sodium nitrate, swapping the ions there. And if you practiced how to balance this equation, this is what your coefficients should have looked like. Number 3, solid zinc added to hydrogen chloride, will a reaction occur? Quick note that hydrogen is not a metal. H2 as a gas can sometimes behave the same way that metals do in the activity series, which is why it is placed there. When hydrogen is by itself at the end of a single replacement reaction, it leaves the reaction as a gas with the formula H2. So hydrogen is not a metal. It is a non-metal. It's kind of found in that strange place on the periodic table up at the top left, but it is on the activity series there. So notice that zinc is more reactive on the activity series than hydrogen gas, than H2. So a reaction here will occur when zinc reacts with hydrochloric acid. We will end up with H2, again, just hydrogen doing a weird thing here, plus zinc chloride ions. So zinc is more reactive, it will become an ion. Here would be the balanced equation for this formula. Number 4, when solid magnesium is added to a lead chloride solution, will a reaction occur? So magnesium is higher than lead on the reaction series. Magnesium is starting off as the solid and lead is starting off dissolved. Since magnesium is more active, magnesium needs to end up as the dissolved substance, and so a reaction will occur. We'll end up with lead plus magnesium chlorate. This reaction was already balanced as it was written, so we didn't even need to add any coefficients. Number 5, when solid barium is added to a solution with sodium chloride, will a reaction occur? Barium is higher than sodium, and so a reaction will occur. If I'm writing those formulas correctly, I'll end up with sodium by itself plus BaCl2, barium chloride ions, and to balance the equation, it should look like this. Again, for the main learning goal for this video, you're just making sure that you identified that yes, a reaction would occur. If you wrote the products and you practice balancing, that's just bonus. Finally, when solid tin is added to potassium nitrate solution, will a reaction occur? I'm going to locate tin and potassium on the reactivity series, and I notice that potassium is above tin. So potassium is already dissolved, it's already in ions, and so no reaction is going to occur because the more reactive substance, the more reactive metal is already dissolved. So tin is not going to take potassium's place. Potassium is more reactive. Hopefully you feel more comfortable with the learning goals from this video, identifying which metals are more or less active, explaining why the more reactive metals will do a single replacement reaction, and predicting whether or not a single replacement reaction would occur.